Hey everyone, welcome back to the channel. Today we're going to talk about the ideal gas law, which is represented by the symbols here, PV equals nRT. And from the ideal gas law, we can derive four different equations from it. And this is Boyle's law, Charle's law, Gay-Lussac's law, and Avogadro's law. Now, if we describe what each of these components of the ideal gas law are, P is for pressure, V is for volume, N is for the amount of substance in moles, R is the universal gas constant, and T is for temperature. And throughout the video, we'll be using another symbol, which is K, and K represents constants. So, for example, most of these will be constants, so N and R are constants throughout. And then, as you can see in each of the equations surrounding this equation, they're only comparing two variables, but there's three variables in the ideal gas law that are still not constants. So when we talk about them, whatever variable isn't being used will be a constant as well. We can demonstrate this with our first law, which is Boyle's law. As you can see here, that P is on the y-axis for pressure, V is on the x-axis, and T is left out, so T becomes a constant here with our other constants N and R, which makes our first part of the equation, which is PV equals our constants. But just saying that PV equals a constant doesn't really help us understand the relationship between pressure and volume. So if we were to try and break this down a bit further to understand it, you can see here pressure times volume equals nRT, which is represented by K. But if we want to put one of the variables on the other side of the equation, for example, volume, what we can do, because it's pressure times volume, is if we divide volume on both sides of the equation, it will eliminate V from the left side of the equation and put V under our constants. So P equals our constants divided by volume. Because it's always constant, we'll just make it a 1, so pressure equals 1 over volume, meaning that there's an inverse relationship, which is represented on our graph here. As you can see that pressure to volume has this line that is diagonal between them that represents that at a higher pressure, there's lower volume, and vice versa. So we've established that for Boyle's law, when temperature is constant and all the other variables are constant, pressure and volume have an inverse relationship. So how does this help clinically for us? Well, in terms of how we breathe with our lungs, as we breathe out, we decrease the volume of our lungs by increasing the intrathoracic pressure. And then we do the opposite when we breathe in. We decrease the intrathoracic pressure, which increases the volume, showing that there's an inverse relationship. Boyle's law can also be broken down a bit further. And when you have two solutions, or for example, a cylinder that holds a certain amount of volume, if you take the pressure and the volume at one point in time, and then there's a change in one of those parameters, then you can actually calculate the change in either pressure or volume on the other side of the equation. So this becomes really useful, for example, clinically, when you want to measure how much oxygen is left in an oxygen tank based on the pressure reading on the valve. The way you would figure this out is that you would have a current pressure on the valve, which, for example, we can say is 7,000 kilopascals. Then V1 would be our oxygen cylinder physical capacity, which I'll just make 10 liters for ease. And then P2 is our atmospheric pressure, which is 101 kilopascals, because remember, this is the oxygen in the tank that is being released into the atmospheric pressure. So you want to know how much volume it's going to take when it's released, okay? Then V2 is our missing variable here. So we can actually put V2 on one side of the equation by making it V2 equals P1 times V1 divided by P2. Now we know that it's 7,000 times 10 liters for the top part of the equation because it's P1 times V1. So this is 70,000. And then you divide it by atmospheric pressure, which is 101 kilopascals, which is 693 liters of oxygen that's in our tank. Now, if we were to halve that pressure, say we've used half the tank, so we've halved the pressure that's left in the tank, so it's 3,500 kilopascals, and then we times it by our volume of the tank, which is 10 liters, making it 35,000 for the top part, divided by our atmospheric pressure, which is 101 kilopascals, meaning that as expected, it will be half 693 liters, which is 346 liters, because we've halved the pressure. So this is how you would figure out how much oxygen is left in the tank, because you know what the starting pressure is, you know what the volume of the tank is, You know what atmospheric pressure is, which is what the oxygen is being released into. So then you can figure out how many liters of oxygen is in the oxygen tank. Now we'll move on to our second law, which is Charle's law. And Charle's law describes the relationship between volume and temperature. So as you can see here, volume is on our y-axis and temperature is on our x-axis. So the constant that we need to use here is pressure. So pressure will join our amount of substance in moles and our universal gas constant in this red box here, and will be represented by K. So to begin this equation, we want to just put temperature onto the same side of the equation as volume. And to do this, because it's our constants times temperature, we can actually then divide by temperature on both sides, which will give us volume over temperature equals our constants. So Charle's law is describing a relationship between volume and temperature. And to understand this relationship, let's get temperature onto the other side of the equation again. So we'll just times temperature to both sides, which means that you can cross temperature out on the left side. It becomes constant times temperature on the right side. Because we're going to make our constant just the number 1 because it doesn't change, we can essentially just cross constant out and eliminate it because it's going to equal whatever temperature is. And we'll bring that down, and then we see there's this relationship that's proportional between temperature and volume. And that's represented on the graph by this diagonal line heading from the lowest points to the highest points for both sides of the graph. So for an increase in temperature, there's an increase in volume, which makes sense because we know that air expands as the temperature increases. This is clinically relevant because when you store gases in cylinders, we know that if the cylinders get hot, the gas will expand, which means that there's risk of explosion or the gas container becoming deformed. The other clinical utility of this is in mercury thermometers, because this doesn't just represent gases per se, but also other metals and other solutions can also expand with temperature. So the mercury thermometer, for example, as the temperature gets hotter or warms up, the mercury will expand and is calibrated to the thermometer based on known temperatures, meaning that you can then figure out the temperature using a mercury thermometer. So it's pretty simple and pretty reliable. And just like with Boyle's law, you can establish a relationship between two variables if you're trying to measure a change, as V1 over T1, so volume over temperature, is equal to V2 over T2, which is the second measurement of volume over temperature. So if you've got, for example, an oxygen cylinder or a gas cylinder, and you know the volume and the temperature in V1, T1, and then you know the temperature in T2, you could potentially figure out the volume that would be in V2. The next equation that you can derive from the ideal gas law is Gay-Lussac's law. And Gay-Lussac's law describes the relationship between pressure and temperature if volume is constant. So pressure is on the y-axis, temperature is on the x-axis, and volume has to join our constants with our substance, with our amount of substance in moles and our universal gas constant. Now, like with our other equations, we want to just move everything over to one side to equal our constants. So we'll just divide by temperature on either side because it's, remember, constants times temperature equals our pressure. So this will equal pressure over temperature equals our constants. So to describe this relationship a bit better, we can do the exact same thing as we did for Charle's law, and we can move our temperature to the other side of pressure, which means that we're left with the equation pressure equals or is proportional to temperature, which is represented by this diagonal green line that moves up and away from temperature and pressure. So you can see here with these circles, if we have the same volume at either end of this line, but we have increasing temperature, we'll have increasing pressure. And this is as we would expect, because we know that if we have a fixed container and we increase the temperature in it, the gas will expand. And if it can't expand the volume like it does in Charle's law, then the pressure will increase. So again, this law is really important when we want to understand how we store gas cylinders, because remember, they're a fixed volume. So if the temperature goes up and the volume can't increase, then the pressure will increase, and that creates an explosion risk as well. Lastly, I wanted to talk about Avogadro's law, and generally when you read about the laws derived from the ideal gas law, they don't always mention Avogadro's law as its own equation. But I just wanted to highlight its relevance here because Avogadro's law describes a relationship between the amount of substance in moles to volume. And this can be represented on a graph as N, which is the amount of substance in moles, is on the x-axis, and volume can be placed on the y-axis as long as everything else remains constant. So constant pressure, constant volume, constant temperature, and using the universal gas constant. To understand this a little bit better, we should first define a mole. And so a mole is a fundamental unit of measurement in the International System of Units that quantifies the amount of substance. And then we've got this number called Avogadro's number, and how that relates to a mole is that 1 mole contains exactly Avogadro's number, which is around 6.022 times 10 to the power of 23. And that's of elementary entities such as atoms, molecules, ions, or other particles. And what this means is that if everything is constant and you have an increasing amount of moles, you can apply Avogadro's number to figure out the exact amount of atoms or particles or ions in that volume, which is represented by V. So there's a linear relationship here. What's really cool about this relationship is that if I have two gases, gas A and gas B, in the same volume represented by these boxes here, with the same pressure, the same temperature, and the same universal gas constant, I can then figure out the amount of moles, and then I can multiply the number of moles by Avogadro's number to then figure out the number of atoms or particles or molecules in each of these boxes, which should equal each other if all else is kept constant. That brings us to the end of this video. We've talked about the ideal gas law, which is pressure times volume equals the amount of substance in moles times the universal gas constant times temperature. And there's 4 major equations that you can derive from this, and that's Boyle's law, which describes the inverse relationship between pressure and volume if temperature remains constant. Then there's Charle's law, which describes the proportional relationship between temperature and volume if pressure remains constant. Then Gay-Lussac's law, which describes the relationship between pressure and temperature if our volume remains constant. And then we discussed Avogadro's law and how this relates to the number of particles, atoms, or molecules using Avogadro's number and the relationship between volume and amount of substance in moles. If you have any feedback or anything you want to add, feel free to leave it in the comments and don't forget to subscribe.